Section 2.2, polynomial functions of higher degree. So we're going to take what we have done in the past, basically. It's a lot of what we do first semester. And just continue doing some work with it and adding some new stuff in. So I want to be able to graph this thing or sketch it. I think I can do this by hand. So I'm going to do a little bit of work here. If you recall from last year, if you have a polynomial in factored form, then you basically can see the zeros looking right at you. So I don't like having a negative in the front inside the parentheses, so I'm going to take it out. And I can take out an x squared from those. So that's going to give me an x squared, and then it's going to flip the sign on that 4 and flip that around as well. All right, this is still factorable. So x squared minus 4, as you know, is a difference of squares, x minus 2x plus 2. All right, I think I'm ready. So, couple things. Domain. Well, it's a polynomial. If it's a polynomial, then the domain is all real numbers. You can plug in whatever you want. It doesn't matter. The range, I think I need a graph. So I'm going to hold off on that one for just a second. So let's write range here, and then we'll just leave a spot for it. All right, what else is going on with this thing? I need to talk about zeros. All right, well, I'm looking at the zeros right now. So it's whatever makes the entire function equal to 0. All right, so the first one, let's get some color coding going on here. So from this first one, that x squared, if I set that equal to 0, then I'm going to get x is equal to 0. But I get it twice because of the squared. So this is with multiplicity of 2. Whenever you have multiplicity, you have to identify that. You can't just say x equals 0. You have to say how many times x equals 0 actually shows up as an answer. All right, then the next one inside the parentheses here, I've had my x minus 2. If I set that equal to 0, I just get x equals 2. Notice there's no exponent on it, so I don't have to say multiplicity. And it's actually kind of redundant if you do. I mean, I guess you can, but it's extra writing. Then with the next one, I'm going to have x plus 2. All right, if I set that equal to 0, I'm going to get a x is equal to negative 2. All right, so I know where my zeros are. That's good. Let's see. Y-intercepts, not so bad. To find the y-intercept, remember you plug in x equals 0. Well, if I plug in 0, then I'm going to get 0 squared times negative 2 times 2. Well, the 0 is just going to annihilate the whole thing. So my y-intercept is just going to be 0. So 0, 0. Increasing, decreasing, extrema, and even, odd, neither. I think I need a graph for this. So I'm just going to give this a quick sketch, but I'm going to type it into my calculator to get a better idea. Now, if this was on the no calculator portion of the test, then all of the things that I have done are fair game. So you can sketch it. It doesn't have to be perfect. You just have to have a pretty good idea of what it's going to look like. And you need to be able to identify domain, zeros, y-intercept, and then hopefully based off of your graph, even, odd, neither. But you can't really give extrema, and you can't give increasing and decreasing because you need the extrema for increasing and decreasing. So if this were a no calculator question, then the only other thing I'd really be looking for is the graph. If this was a calculator question, then I could ask for the range and increasing, decreasing, extrema, even, odd, neither, all that business. So I'm going to go ahead and type this into my calculator and see what I get. So here are the keystrokes I'm going to follow. I'm going to go to my y equals button. Then I'm going to go to my y1. Actually, I'm going to clear out everything that's there. At this point, it doesn't matter if you type in the factored form of the f of x or the original f of x. Your calculator will be able to do the work for you. So I think that with ease, typing in the first one would probably be a little bit simpler than the second one. So I would type that into my calculator. Then, after I've done that, remember I'm going to try that zoom fit thing again and see if I can get it to do what I want it to do. Or, another thing that you can do, if you want a standard window of negative 10 to 10, you can do zoom standard. I think it's Z standard on the calculator. Basically, this just uses the window, excuse me, from negative 10 to positive 10. So I'm going to type that in. and pause, so I would do the same if I were you. Okay, so I went ahead and typed this in. Let's take a look at what this thing looks like. So I'm going to go ahead and set up my axes. And again, for me, this is just a sketch. I want to make sure that I hit my zeros appropriately, though. So let's do increments of 1. And I know that my zeros are going to be at 0, at positive 2, and at negative 2. Now, just based off of the equation itself, so let's call this 1 also. Based off of the equation itself, I want to talk a little bit about end behavior and leading coefficient test. So I take a look at this, and I know that the degree of this polynomial, so going back to my original non-factored form, if it's all multiplied out like it is with the given, all you have to do is look at the highest exponent. That tells you the degree of this thing. So I know that the degree of this polynomial, I'm just going to go ahead and put it in my list, is 4. Because it's an even number, I know that both tails go in the same direction. All right, that's one thing. Then I need to go back and take a look at the leading coefficient. All right, so the leading coefficient is negative. All right, so that means that both tails are going in the same direction, and they're both going in the negative direction, which is down. So I know that my end behavior on this is going to be both tails down. Or you can say falls to the left, falls to the right. All right, so this gives me a pretty good idea. So I can go back to my graph. And again, I'm just sketching it here. So I would say that it's going to go down on both. I have multiplicity at 0, which means it's going to bounce at 0. So if I sketch this up, bounce, up, back down. So I would say it looks something kind of like that. Now I may need to change my increments on the y-axis because I haven't looked at that yet on my calculator. I am just giving this thing a decent sketch, so let's get rid of that 1 in there. So I'm not sure what those increments are going to be just yet. All right, now back to the calculator. So now that I have my picture in front of me, I should be able to do everything else, but I need to find the extrema here. So I know one of them already. I can tell you what the relative min is because I'm looking right at it. That's the only relative min. So my relative min is going to be right at that bounce, which is 0, 0. So I can go ahead and write that in my list as well. So let's get to our extrema. So I know that my relative min is going to be 0, 0. Because there's no other point on there that represents like a dip in the graph or a valley in the graph. Now, for my max, I'm going to grab my calculator. So, to calculate my max, here's what I'm going to do. Here are my keystrokes. And I think I'm going to do this one like a darker purple. So for this maximum, what I'm looking for is this maximum right here. So, my keystrokes. I'm going to go to my Calc button. So for this, I'll go to Calc. After you go to Calc, you're going to select Maximum, which for me is option 4. And hit enter. So hit enter when you get to the maximum part. After you've done that, it's going to take you back to the screen where your graph is, and it's going to ask you for a left bound and a right bound. So you're going to use your arrow buttons, left and right, so that you can get to the left of this point. So I am going to take my cursor and I'm going to mark on the left here. So I'm just going to arrow over until I get there. And then I'm going to hit enter. So from here, hit enter. Then it asks you for the right bound. You're going to do the same thing. I'm going to go over to the right of the point and then I'm going to hit enter. Then it asks you if you want to guess. Well, no, I don't want to guess. I want the thing to do it for me. You don't have to move your cursor at all when you're calculating extrema when you get to the guess part. Just hit enter again. So it's going to say guess. After you've done the right bound and the left bound, just hit enter on that. It'll tell you. Now from here, it tells me what the max is. So for this point, it gave me negative 1.4142, 4. All right, so I have one of them. So for my relative max, I know that one of them is going to be the point I just got. I'm going to follow the exact same strokes to be able to find the one on the right-hand side. Now, I am going to pause and calculate it, and then I'm going to write it down. I would pause if I were you, do the calculation yourself, and see if you get the same answer. Okay, when I calculated, you'll notice that I put the marks in green on my picture. I got almost the exact same point with just the signs changed on the x's. So 1.4142, 4 as my other relative max. All right, so now I have those covered. All right, next thing we need to do is to do our increasing, decreasing, and even, odd, neither. All right, so, we need to do the range also. So let's go back up to our range. Looking at my picture, this graph goes as low as negative infinity and as high as my max. If you take a look at my max, the highest y value this is going to attain is 4, and it hits there, so put a bracket. So my range is going to be negative infinity to positive 4. Remember that for domain and range, we always go small to big. Make sure that you keep the order correct. If you do big to small, it's going to be marked wrong. All right, now let's put our points right here on here. So I'm going to go ahead and identify my purple and my green on my picture and then start doing increasing, decreasing, and constant. Okay, I went ahead and identified my purple and my green extrema as well as my min on there as well. So what I'm going to do is I'm going to take a look at my graph and check the behavior as I come in from the left. So from the left, so negative x values, the graph is going up, so it is increasing. So as I come in from the far left, the graph is going up, 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 up until I get to the first relative max, which the x value at that relative max is negative 1.4142. Immediately after that maximum, I'm going down, so now I'm decreasing. Immediately after that maximum, as I approach the minimum, the x at the minimum is 0. Immediately after the minimum, I'm now going up again. So I go back to my increasing. Immediately after the minimum, as I'm approaching my maximum, the x value of my next maximum was 1.4142. Immediately after that maximum, my graph is now going down. So as my x's get bigger and bigger and bigger and bigger, my y after 1.4142 x value is going to get smaller and smaller and smaller and smaller. Notice that my increasing and my decreasing are always in terms of the x interval. The name increasing and the name decreasing is already telling you what the y's are doing. It's telling you that the y's are going up or that the y's are going down. So whenever we do this, we always do the x interval for the name themselves. All right, last thing we need to do, I think, is even, odd, neither. So to do even, odd, neither, we can just take a look at the graph, and I already think I know what it is. But let's go ahead and do the algebra part of this. So take my original function that I started out with, sorry about that. Apparently the neighbor dogs didn't like mine. So we have our f of x function, original, and remember to determine even, odd, neither, we're just going to plug in negative x and see how it compares to the original. So every to where I see an x, I'm just going to plug in a negative x and see what happens. Do the math, and looks like nothing changes. It looks identical to the original f of x function. Because of that, I would say that this function is even. So now, since f of negative x is equal to f of x, we can say this is an even function. We can also see it in the graph, because if you fold this graph over on top of the y-axis, the left and the right-hand side match up perfectly. That's another way to determine if a function is even, odd, or neither. Okay. All right, next question. Want to write a polynomial function of least degree with integral coefficients given the following zeros. All right, so since these are zeros, let's go ahead and write them out as x equals, each one of them separately. And then with that last one, 2 plus root 7, remember the only way you can actually get a 2 plus root 7 is from the quadratic formula or from completing the square. And every radical comes with a partner, and that's its conjugate. So although it's not in the list, it has to be included. Now, what I'm going to do is write each one of these as factors. To get a factor, you actually set them each equal to 0. Although the first one is done. The second one, we're going to have to add the 5. And then the last two, we're going to subtract the stuff over. So to get something as a factor, you want it equal to 0. Now, I want this thing in expanded form. To get it in expanded form, I'm actually going to have to multiply all these together. So let's call my function f of x. And I'm just going to take each factor and multiply them together. Choose the two factors that you want to multiply together. Remember, we can only handle multiplication of two things at the same time. So just make good choices here. And it really depends on just whatever you think is easier. For me, I like multiplying the conjugates together because that means that the radicals would disappear. So I'm going to go ahead and multiply those together first. So I don't use the boxes when I multiply these out, so I'm just going to end up plopping down the answer here. So if you want to pause, right now would be a great time. Multiply it out yourself, combine like terms, see if you and I get the same thing. Okay, so in orange is my multiplication of those two factors. And then I think I'm just going to go ahead and multiply the first two together as well. Since I got to multiply all four of them eventually, I'm just going to pair stuff together that I think makes sense to me. So if I put those together, and I'm just going to bring it down because there isn't going to be any combining like terms business on this one. And then the last thing that you need to do is multiply this out. So again, I will FOIL it out. I don't use the boxes, but you and I should get the exact same answer. So I'm just going to go ahead and multiply these out. My first multiplication, and I'll pause this for a second. You might want to pause, do your multiplication, and see if we get the same thing. Okay, so I multiplied mine out, did my foiling, or basically distributing, and then I just combined like terms. So here is my polynomial function, decide to call it f of x, with integral coefficients. What that means is that you don't have any fractions. That's all. No fractions, no decimals. Everything is an integer when you multiply it together. So I've got a 1 on my x to the fourth, a 1 on my x cubed, a negative 23 on my x squared, and a negative 15 on my x. Every single one of those is an integer, so integral coefficients. Okay. All right, our application problem for this unit. So I already have the question written down, at least the first part. So we have our open box. This is the exact same question that you have in your notes already. I didn't write anything differently. The picture doesn't look as splendid as the one in the notes does, but I think you get the general idea. Plus you have the picture in front of you. We want to verify that the volume of the box is given by the function, and we have it right there. So what we're going to be doing is we're just going to be doing volume of this thing. All right. So I know that volume, by definition, is length times width times height. Whenever you're talking about a rectangular-based box. So go back over to my picture, and I would say that the length I'm going to have is across the top here. I would also then say that the width is going to be this one. And then my height is actually going to be in the other picture. So it would be the height of the box itself. So that is going to be, I guess in our picture, the distance in here. All right, so I know that the length, well, the entire length is 24. That's what was given to me. But if I take a look at the picture, as I keep taking up X sections on the side, you'll see over here, I'll go ahead and highlight it in like a pinkish color, that out of the 24 across the top, I'm going to have 2 X's taken out on each side. So I'm going to have 2 X's subtracted, and then another 2 X's subtracted. One for the right side, one for the left side. All right. Then my width is also going to be 24. But this time, it's not going to be 2 X's that are getting subtracted. If I just take a look, it's going to be this 1 X here that is subtracted on each side. So I'll be subtracting an X based off of my picture, like across, up on the top and down on the bottom. All right. Then, based off of the other picture that was given to me that's in your notes, the actual height of the box, that's just going to be a single X, just one of them. All right, so now let's go ahead and combine like terms, because this thing does not look at all like what they want me to prove it is. So combine those, I get a 4X. Combine those, I get a 2X. And then don't forget the X. All right, I see GCFs here. So out of this first one, I'm going to take a 4. It's going to give me a 6 minus X. Out of the second one, I'm going to take a 2. That's going to give me a 12 minus X, and then don't forget about the X. All right, now from here, I'm just going to take those guys that have all been pulled out of the parentheses and just kind of put them all together. So 4 times 2 times X, that's going to give me an 8X. And then 6 minus X, and 12 minus X. And compare this to what they want me to prove that it is, and the match. This is good. Okay, so there's my volume. Now let's take a look at part B. Okay, so second question, well, second part for this question, same one in your notes, we're going to determine the domain of the function. All right, well, if I think about volume itself, the lowest volume I could get, not technically 0, but pretty darn close to it. So I think I'm going to take my volume and I'm going to set it equal to 0, knowing that that is going to be the lowest it could possibly be, or at least really close to it. And I'm going to solve for X. So this first one says that X is 0. The second one says that X is 6. And this third one says that X is 12. Now, remember that X in this case represents dimensions. So we need to make sure that we have dimensions that can actually exist. So I can't have a dimension of 0, but I could have a dimension of like 0.000000001. So I have something really close to 0, but 0 itself doesn't make any sense. And If I plugged in 6, I can have a dimension of 6, there's no problem with that, and then a dimension of 12. All right, well, let's think about realistically between these things. So if I look at dimensions between 0 and 6, would that still give me a positive volume? And I would say, let's only pick one of them or two of them, or even just look at the equation and try and see if you can inspect it a little bit. So let's say that our x dimension is 1. Will that still result in a positive volume? So let's say we want to find the volume of a dimension of 1. So I'm just going to plug 1's in. And I'm not going to do the math, because by looking at this, I'm going to get 8 times 5 times 11. This is a positive number, so I would say that 1 is going to give me a positive value. 2 will also do the same thing, so I'll get 6 minus 2, which is positive, 12 minus 2, which is positive. Okay, if I go to 6, 6 is going to be a problem because it's going to give me 0. But if I do 5.99999, I still get a positive number. So I would say that a little bit bigger than 0 is good, smaller than 6 is good, 6 is no good. We'll see what happens when we take a look at the next part from 6 to 12. If I choose any number between 6 and 12, let's say 7, if I plug in 7, then I'm going to get 56, 8 times 7, positive number, good. 6 minus 7. This is bad. 6 minus 7 is a negative number. If you plug in 7, you're going to get a negative volume. That doesn't make any sense. So from 6 to 12 is no good. But from 0 to 6 is pretty good. Just make sure you don't include the 0 or the 6. So I would say that my domain is not quite 0, but pretty darn close, and not quite 6, but pretty darn close. You just want to make sure that the dimensions that you're getting are positive and that your volume is also then going to be positive. Let's take a look at the next part. Okay, so we have the next part, question C, that goes along with this one. And I want to sketch the graph of the function and determine really where the maximum volume is. All right, so I'm going to do exactly what I did in previous notes with some calculator-driven problems. So first thing I'm going to do is I'm going to go to my y equals button. And I'm going to clear out anything that's in there, and I'm going to type the original function into my y1, my v of x, the one that I found out. So that's going to give me 8x, 6 minus x, 12 minus x. So type that in. Now we already know what the domain is. We don't want to look at anything outside of 0 to 6. So the next thing that I did was I went to my table. Oh, no, I didn't. That's a lie. I went to my table set. On my table set, I decided to start my table at 0. And I decided to do my delta table as 1, just to start. Then I went to my table. So I had to set my table first. Looking at my table, it's now going to go 0, 1, 2, 3, 4, 5, 6. I don't even have to scroll. And I'm looking for the highest y value. Well, based off of going by increments of 1, the highest y value I see is at 3. So, and I'm looking at the values on my table itself. So I would see that I think 3, 648, somewhere in that ballpark. All right, what this does is it allows me to figure out what I want my window to be when I graph. So now I'm going to go to my window button. On my window button, I'm going to set my x minimum to 0, my x maximum to 6, so my actual domain. Then I'm going to do my y minimum to 0. And then taking a look at what the y maximum was for 3, I'm just going to go up to 650 as my y max. Then I'm going to hit my graph button. Now that I've done that, I can see most of the graph here, and it looks like my 650 wasn't high enough, but I can still calculate the maximum without having the entire picture in front of me. All I need is the left bound and the right bound. So from here, I'm going to pause. I'm going to calc my maximum. It gives you practice from the last section as well. And let's see if we get the same value. Okay, so I wrote down the rest of the strokes that I had talked about with the x-min, x-max, y-min, y-max, graph, calc, maximum. I'm not going to go through the strokes again with maximum. Give you a little bit of practice on this. And when I typed this in, I got 2.5358, 665.1075. Remember that the first part represents my x value of the maximum. And the second part, remember the y equals, we allowed to represent the max this is the volume. Okay, so a little bit more practice on application problems.